Okay, so we've talked about the bookends, define my mission, affect my environment, go from A to B or C or D and return. All right, so we know where we are in the world, we know how to get there, but what does our world look like? How do we move around in it safely? How do we know what the environment is? And for that, Kevin is going to educate us about part of this magic in the middle.
Hello everybody, my name is Kevin French, and I'm from the University of Florida. And today I'll be talking about object detection and tracking. And so again, we in this lab use an agile workflow, and this is one of the charts that we would use to present our work every 2 weeks. And the agile workflow is really awesome. It lets us, everybody stays on touch. We talk about things that are holding us back, and it lets everybody collaborate. And if we need to make changes, we can make them quickly and agilely. And so it's been really great, and this is one of my last charts that I have presented. So, as per the mission, what am I doing? I have written software to dynamically plan around an obstacle. And so, well, actually, I'm detecting and tracking that obstacle. And so, part 9 is we're going to have another UAV that is in our flight zone that we need to get around. And so what I'm going to talk about today is what object detection and tracking even is. And then on top of that, how it works, why is it useful, how I got here, and some lessons I've learned along the way. So what is object detection and tracking? Well, first and foremost, how do we see the world? For us, we're going to use a LiDAR. And that basically takes two-dimensional scan of the world, this particular LiDAR does. And as you can see up here behind me, those are the little red dots that are actually quite hard to see underneath of the squares and the spheres. And so that is just the raw data. That raw data is then transformed into something that the software can understand. And then the state of each of those objects or targets are being estimated. And that is the object detection part. Then we need to track these objects. And as you can see behind me, I'm the green sphere closest to the little marker in the middle of the screen. And that software is tracking my movements. And as you can see, my color does not change as I move, meaning that I am the same object. And that's the tracking portion. It keeps track of what is what. So how does data flow through my system? First, we get raw data from the LiDAR, which the LiDAR picture you see there is this object sensor right here. Once we have raw data from the LiDAR, we then have to register the data, which simply means put the data in a frame of reference that the software can understand. So for us, that's an XYZ coordinate system. Then after we have registered the data, we want to extract targets from that. And that is essentially just grouping data together and deciding which ones correspond to a single object. And we'll go into some more detail about that in this a little bit. Then after the targets have been extracted, we want to send those targets to data association. And in data association, we decide what measurements belong to what targets. And then from data association, that goes to the output where other systems can consume the data, and also it feeds back into itself. So how did I structure this? It's actually quite interesting how I had to do this. So per the agile flow in here, I actually came in not knowing the software we use in this lab called Data Distribution Service. And DDS, so instead, I already knew Robot Operating System, ROS. And so I developed in Robot Operating System because I could very quickly develop my algorithms, and then also ROS has a lot of cool tools that are really useful. But ultimately, I had to move it into DDS because that is what we use here in this lab. And so I designed a bridge that actually bridges between ROS and DDS. And it's pretty impressive, the bridge that I made. It is able to transfer data both directions and transform the information from message types that only exist in DDS to message types that only exist in ROS, and the other way as well. So this bridge also is powerful in the fact that DDS understands geodetic coordinate systems, which is latitude, longitude, and altitude. But ROS doesn't really have good tools for working in geodetic coordinates. It uses X, Y, and Z in a local coordinate frame. So the bridge took care of that for me. The bridge that I designed actually transformed the frames of references so that ROS could understand DDS and DDS could understand ROS. And so that's kind of how I structured my code. And the bridge is also designed so that individual components could be moved from ROS to DDS or from DDS to ROS without really incurring much difficulty in adjusting the bridge to handle that. So, and here is a video demo of the software, the output of the software being used to track the mothership that we see right here. What you're seeing is the ship, the OG1 right here, was suspended via wire and spinning in the in this flight area. And as it turned, it picked the closest and the closest object within its view and sent that over to the camera for the camera to start tracking. And that's what that red square is. And if you could read it, that number along the on the picture corresponds to the number that is the unique identifier of this target right here. And I'll show you that up close in just a second. So I've been throwing around the words target and object quite a bit and some classifiers for the word target. And I'm going to explain what the heck I mean. So an object is a physical entity in the environment which we are measuring. But a target, this is a self-definition, is an object that has been measured and exists in software now. So from there, a raw, new, or measured target is a target that has been taken from a measurement and extracted and now exists in software, but it has not yet been through the data association process. So what is data association? That is the process of relating measurements together to be from the same object in the environment. Then potential targets are targets that are targets that have been associated with at least one raw measurement, and then these, but they haven't been around long enough for them to be a permanent target, which once they have been around long enough to become a permanent target, they're considered a track target. And these more permanent targets are the ultimate output of the algorithm. And what you're seeing up above me is basically all the permanent targets. Now, potential targets live for a little while, but it's a relatively long period of time in software. But in real life, it's only a couple milliseconds, and we can't see that fast. So if you could, you'd see potential targets up there, and they're see-through, and that's how you can tell them apart. But you probably won't see any. They go too fast. So what is target extraction? Target extraction is the process of actually grouping data together. In this case, we're doing it by how spaced apart things are. As you can see up on the board, I am completely separate from everything else around me, and so the points that correspond to my measurements from the LiDAR are grouped into a single object. And it tracks me around and keeps extracting the data for me. And once so then once we've actually done that extraction and grouped points together, then we find its centroid in a bounding box, and that becomes a representation of a target. And to show you here, we have what I've taken a picture of is the mothership and her cone flagships. And I will actually reproduce this picture you see right now by rotating OG1. So now you can see on the board the pink target is mothership, along with the two targets on its side, the more teal and whitish colored targets. Those are the cone ships on the side. And so you can kind of get an idea of how the robot OG1 sees the world. So now I'll turn it back towards us. So now, how does the data association process work? This is where a lot of the meat of the algorithm comes in, and the most interesting component. And so the first step is we take any measurements that we take, any targets that we've extracted, and they can only be associated with another target, a tracked target or a potential target, if they're within a windowing distance. In this case, it's a 1 unit, whatever that unit may be, normally meters. Then the closest match is always chosen with the restriction that the target, the new measurement, can only associate with one and only one tracked target. It makes no sense for, say, mothership to be, the measurement associated with mothership to be associated also with the cone ship. That makes no logical sense, so that restriction is imparted. Along with new targets that have no match to tracked targets become potential targets, as you can see in column T3. So then also, tracked targets without a match self-associate, which means that there is no good measurement in the environment that associates with a tracked target. And if a potential target is associated repeatedly for a long period of time with new measurements, that potential target becomes a target. Then, if a tracked target or a potential target self-associate with themselves for a long enough period of time, it gets erased, because it probably doesn't actually still exist in our environment. And so, what is this useful for? Why do we care? There's so much that this can actually be used for. For example, obstacle avoidance, object classification, staying in a formation in a swarm, and doing following behaviors. And so we actually went ahead, well, I actually went ahead and implemented 2 of these. So I implemented obstacle avoidance and camera target tracking initialization. And to show you this, obstacle avoidance, essentially what I did was I took the tracked targets out of my algorithm and used those targets. I transformed them into the geodetic coordinate system that DDS uses, the Aeon DDS. And in Aeon DDS, those can then be fed into a path planner, which can take in information about how the obstacle is moving, where it is in the environment, and be able to move around, plan around it. And the benefit of using the object tracking algorithm and not just raw data is that, as you can see, I am persisted. I am constantly on the screen, never moving away. My color stays the same. And so these objects are persistent, and they're not going to just flash away for 1 second. The path planning algorithm is like, oh, I can probably go through there now. And then the next timestamp returns. Instead, if we miss a measurement, it's okay. The data will be persisted. And we can also start to grab information about the kinematic states of the object, whether it's going this way or if it's going this way. And then the path planning algorithm can use that information to better make plans around how to avoid the obstacle. Then I implemented camera target initialization, which is where I took the data from the output, the tracked targets, and I sent that over to a camera, which was able to then transform the data into the camera space, letting me, any targets in the view space of the camera would be transformed and marked in the camera space. So that you see the 3 red squares on this image, those are all marked to the 3 targets in this in the LiDAR view that actually map to the pixel space. The other 2 targets are not in the view space of the camera and therefore are thrown out. And as you can see, it works pretty well. Target 61 is myself, 128 is Erica, and 106 is Spencer. And the benefit of this is that initializing a target track in the camera space is computationally intensive, and it takes a lot of processing power for it to be able to find something interesting to track. Whereas with the LiDAR, you don't have to do that. Everything is pretty much interesting. So you can take the most interesting thing from LiDAR and use that as where you start your camera tracking. Now, how did I get here? Well, started out with a lot of literature reviews and trying to understand the problem space. And then we picked out some algorithms and we tested them. And one of the most interesting ones, we were really interested in how we could apply neural networks to this problem. And we picked a solution that used a Hopfield neural network. And in implementing the Hopfield neural network that was designed for radar, we quickly realized that it wasn't going to function the way we expected it to. However, we realized that at its base, there was a nearest neighbors algorithm inside. And so we stripped away and that nearest neighbors algorithm part worked really well. And so we stripped away the Hopfield neural network and just used the nearest neighbor. And it worked really well. And then, as I mentioned earlier, I'd started that all out in the robot operating system and started actually moving it over to DDS. And once I had learned DDS, I actually started making entire pieces of my software in DDS, Aeon DDS, which Aeon is our software. DDS is the data distribution service, and we use that in Aeon. Then the other part is I actually did not start out on OG1. I started out on much smaller vehicles on a bench setup that was not designed to fly, using smaller indoor LiDARs. And then also cameras to do the camera tracking initialization. And from there, I upgraded to OG1 with outdoor LiDARs that go much farther and much more powerful and much faster. Actually flew it. And I learned a lot of lessons along the way. So obviously, communication is always essential. I also learned that the number 12 is much greater than 5. And it's interesting the way I learned that. So the bench setup here you see was set up originally to work with this LiDAR, which takes 5-volt input. However, the larger outdoor LiDAR requires a little bit more oomph, and it requires 12 volts. And so when I was setting up to start testing the new LiDAR, I had another PI change the voltage on the output for me, but I forgot, and I never ended up using this. And so one day I needed to go back to my bench rig to test something, and I plugged in my LiDAR, the small LiDAR, which only took 5 volts, with 12 volts. I turned that off pretty quick after I smelled the burning. Lesson learned. From now on, we're going to mark voltages and do some configuration management for everything we do. And another important lesson I learned is it's way easier to debug inside in nice air-conditioned test environments instead of out in the windy, cold, sunny outdoors where you can't see your screen because of the sunlight. Much easier to debug indoors, more comfortable. And I'd like to thank everyone here in the Autonomy Incubator. You guys have all been wonderful. And a special thanks to Jim and Locke for mentoring me. And then a special thanks to all the other interns who've made this experience wonderful. And then a special thanks to Jada and Christine for setting everything up. All right, thank you very much, guys. The question is, why did we start with a Hopfield neural network versus any other neural network? Well, there's a lot of research in this area, but I found that a lot of different, the Hopfield neural network is well designed for this problem, and some other people have had some success using it. And so we went ahead, and because there was a good amount of people who actually use the Hopfield neural network in this space, we decided to try it out. And a lot of other neural networks are just too beefy and unnecessarily so for this, like convolutional neural networks. They're really well designed for image processing, and we're not image processing. So we decided to go with the Hopfield neural network, and actually we went with a competitive Hopfield neural network. But again, as I said, it ended up not working. So there's some more research to be done in that field. The question is, what was the greatest challenge that I had to face this semester? That's a good question. definitely moving from ROS to DDS. That was hard.
So you might, yeah, so on that, you mentioned Aeon DDS.
Yes.
Real quick.
Yeah, of course. So in the lab, our software, we call it Aeon. And so Aeon DDS is our specific use of the data distribution service. And so when I mention Aeon DDS, I mean our software that we designed around data distribution service. And also Aeon has a lot of other tools and functionality that we already have.
And it stands for?
What does Aeon stand for?
Yes.
Uh-oh, I'm on the spot now.
A is for autonomous.
Huh?
A is for autonomous.
Autonomous. Wait, I thought it wasn't just a Greek word. You guys are pulling my leg, aren't
It's a
you?
trick deal.
It's Autonomous Entities Operations Network.
Autonomous Entities Operations Network. That's what that stands for.
So to actually expand on that a little bit, that is the architecture and the framework that we've developed here in the Autonomy Incubator that allows for plug and play integration and testing of software algorithms, different hardware type sensors, so that we're not limited simply to a point design. You can swap capabilities in and out as you need depending upon the mission, or maybe the need of a customer who might want to come in here and test their algorithm or test their new sensor.
Yeah.
All right, any more questions for Kevin? One more round of applause. Thank you, Kevin.
Thank you.